two rods of two uniform rods A and B having same dimensions. So that means same length, width, thickness, etc. Same dimensions, but made of different materials of densities dA and dB. So they have different densities. The rotation kinetic energies of the rods are same. So the rotation kinetic energies are same. Then the ratio angular momentum of A to the angular momentum of B is given by. Okay. Try to get the answer for this. Why is this breaking? How about now? Is it still breaking? All right. If it's anything, if it's not clear, let me know. Okay, so try to get the answer for the 11th question. Did you get the answer? Okay, so here it says the kinetic energies are same and we want the ratio between the momentum. So I write the kinetic energy. What is the rotation kinetic energy? That is given by half I omega squared. Okay. So now in this equation, what I'm going to do is I multiply by I and divide by I. Okay, we'll see. Okay, so then here we get E equals, here I squared omega squared. In the numerator, I can write as I omega squared over 2y. Okay, so then this one we can write E equals, sorry, here I can write E equals, now I omega is the angular momentum, right? So I omega is the angular momentum, so L squared over 2y. So now hereafter you should know this relation. Okay. Okay, so then now I can equate the rotation kinetic energies. So it says EA is equals to EB. Okay, so then we can write EA is, we can write LA squared over 2I. So 2 times IA. And here LB squared over 2 times LB. Now, if you have already done this kind of question, then if you have this knowledge, then this is the first thing you will write. I mean, to answer to this question. Okay. So you have to train yourself up to that level. All right. So now we can write here, we want to get the ratio of LA to LB, right? So here this 2 and 2 cancel. So we have L cross multiplication, LA over LB, LA squared over LB squared is equals to IA divided by IB. Okay. LA squared is equals to IA. LA squared over LB squared is equals IA over IB. Alright, now we can write. So here LA over LB whole thing squared. So I is, now it's a rod, right? Rotating by the midpoint. So from midpoint means 1 over 3 m L squared, right? The length is L. Okay. So here 1 over 3 m A L squared divided by 1 over 3 mb L squared. Then we have this cancel, L squared cancel, ma over A for both because same dimensions. So therefore we get LA over LB is equals to dA over dB square root. So the answer is the fourth one. Yes, so your answer is correct. Good. Okay. So let's move on to the next question. Okay. 3 wheels A, B, and C of the same mass and same external radius are made out of uniform sheets of different materials shown in the figure. These wheels are released simultaneously from rest from the same height at the top of an inclined plane. Your internet connection is unstable. I just got a notification. Let me know if my voice is breaking, okay? The wheels rolls down without slipping. So without slipping means it's rolling under static friction force. Okay, that means the force friction acting on the wheels are if I say that if it's the friction force, it will be less than the static limiting friction force. So they will roll without slipping. Okay. The wheels roll down without slipping. The order that they will reach the bottom of the inclined plane as first, second, third respectively is. So we know that if I is large, if I is greater, greater the inertia, greater the time, right? We did this in the last class, isn't it? So we compare the inertia of these materials. Okay, so you can see A has the greatest inertia, IA is the greatest, and then IC is second, and then IB is the smallest. So A will take the larger time. The order they will reach the bottom of the inclined plane. So larger time A comes last, and then C next B. Okay, so the second one, your answer is correct. Very good. And do the 13th question. A uniform circular disk of radius RNM rotates with the uniform angular speed omega in a horizontal plane about an axis passing through its center perpendicular to its plane. The moment of inertia of the disk above the axis described above half mr squared. When a ball of clay of mass m over 8 is placed gently on the edge of the disk and if it sticks, the new angular speed of the system is. Now, when they are saying gently, meaning that no external force is applied when keeping this mass. Okay, so we can see here the disk rotates. So its mass is m, radius is r. Okay, so initially it rotates with omega. So we can write I angular momentum conservation. So therefore I1 omega is equals to I2 omega 2. So I1 is half mr square into omega is equals to I2. Now we have to add both the inertia after adding that mass of mr square plus the mass of that is m over 8. So m over 8 r squared. Since it's a point mass, a small ball type of mass, so its inertia, moment of inertia is simply mass times the distance squared times omega 2. Can you see the screen? Alright, but it's not appearing to me on device. Well, connection is unstable. Okay, so here we have so I1 omega 1 is equals to I2 omega 2. So I1 is half mr squared into omega. I2 is half mr squared plus m over 8 r squared into omega 2. We want to simplify this. Right, so we can divide mr squared, mr squared, mr squared. So here we have in the left hand side half omega equals to here half plus 1 over 8. So 8 is the least common multiple. So 2 into 4, 1 into 4 is 4 plus 1 into omega 2. So therefore omega 2 equals half omega times 8 over 5. So it will be 4 over 5 omega. Third one is the answer. And what was your answer? Third, very good. All right. Very good. And do the 14th one. Why is this breaking again? I think I'm having a connection issue. Do the 14th one. By the way, to answer the 14th question, you should have a knowledge about circular motion. Have you done circular motion in school or anywhere? No. Okay, then I'll explain this question. Um, it's actually a combination of both circular motion and rotation motion. A circular disc-shaped pinwheel type firework shown in the figure performs rotation motion about the axis on a horizontal smooth floor due to a constant reaction force generated by its burning. So you can see it's burning. So that means this burning air makes a force on air. So equal and opposite reaction force acts on this thing. So it will rotate. Right. So I'll mark the force acting on this, and it says this force is constant. So constant reaction force generated by burning. Assume that the pinwheel retains the shape of a uniform circular disc throughout its moment of inertia. So the moment of inertia is given mr, omega, alpha values of radius, angular velocity, angular acceleration, respectively. Okay, so we want to find which is constant. So since so the center, this force is mm, yeah, so we can write rho equals I alpha. I think no need of circular motion. So we can write rho equals I alpha, and also rho is the force times the distance. Radius r is equals to I alpha. Okay, so we'll simplify this. So force into radius equals to I. So it's a disk. you have to consider shape of a uniform circular disk. So half mr squared is the I into alpha. Okay. So then if you simplify this r and this r cancel. So F equals half mr alpha. So therefore, since this force is constant, this quantity should be constant. So mr alpha is constant. This one is the answer. Is that clear? Okay. Do the next one. The two uniform disks A and B shown in the figure are made of the same material and have equal masses. The radius of the disk A is greater than that of B. The disks are kept in isolation at outer space. Consider the following statements. The disk A takes longer time than B to gain a given speed under an external force acting through the center of the disk. Okay, so here, let's see. Okay, it says one. Okay. Now let's check the statement A. The disk A takes longer time than B to gain a given under external force acting through the center. Okay, so we can write tau equals I alpha. Okay, tau equals I alpha, and it says under an external force. So we'll consider how alpha relate with force. So T equals tau equals F into R equals, it's a disk, so half mr squared is the moment of inertia into alpha. So this R and this cancel. So F equals to uh, half mr alpha. Okay, so F equals half mr alpha. So if F constant, so under an external force, so same force, if we keep F constant, the mass is also given that it is constant for both. So we can see if R large means alpha is small, therefore A will take larger time, longer time than B to gain a given speed under, yes, so A is correct. Okay, because you can see here for A, R is large, so larger so moment of inertia is large. Okay, so therefore alpha will be less, angular acceleration will be less, So it will speed increases slowly. Okay. So therefore statement A is correct. The disk B takes a longer time than A to gain given angular speed under an external torque about the axis of its. The disk B takes longer time than A to gain an angular speed under an external torque. Okay, so we can write tau equals I alpha, right? So we have tau equals I is half m r squared, alpha is omega minus omega naught over t. So the disk B takes longer time. Okay. So initial velocity is zero, so we can directly omega over t. M is constant. R is large for A. So therefore, alpha will be small. Else I can, yeah, just think of alpha. Just tau equals I alpha. M constant. R is large means alpha will be small because under an external torque, so we keep the torque constant. So mass is also constant. R large means alpha will be small. The disk B takes longer than A to gain a angular speed. Okay, so for which for A, R is large, so alpha will be small. So the statement B is wrong. The disk B has higher rotational inertia about the axis of disk than disk A. The disk B has higher rotational inertia about the axis of the disk than disk A. So B has less inertia compared to A, so only A is true. Is that clear? Aviation, is it clear? Okay. 16. Okay, let us see that. So first we have a rough inclined plane and a sphere, and it is rolling. Okay, so the friction will be here this side. Normal reaction force from here. Weight. So F R mg. We can take the torque about point torque. So we can write tau equals I alpha. So and also tau equals Ft. So F into D equals I alpha. So this distance is the radius. So F into R equals I alpha. Okay, so then alpha will be Fr over I. So that is alpha. Now on this point, if it's rotating with alpha, the acceleration of the center of mass is given by um, A equals R alpha. So therefore A equals R into alpha is R over I. Okay. So A equals R squared over I. How can I relate this to? Okay, so that is the acceleration. Now, in the next one, it is placed on a smooth plane. Okay, so here uh, it moves due to the weight component, it slips down. So that is, let's say the angle of inclination is theta. The angle, same inclination theta, so the next component is mg sine theta. So A is equals to g sine theta. Let us take this A1, and here A2 is equals to g sine theta. Okay, so here I want to compare A1 and A2. So then I will take this A1, which is F. F is equals to, so it's rolling means the force is balanced. Okay, so this F equals mg sine theta. So F equals mg sine theta times r squared over I. And you can simplify this further. Mg sine theta times r squared over I for disk is half mr squared. Half mr squared. So r squared cancel, m cancel. So A1 is equals to 2g sine theta. So when it is rolling, the acceleration is twice. So A1 is equals to 2 times A2, right? So When it's rolling, it has a large acceleration. That means it will reach soon. So, okay, starting from rest, here takes time t to roll down. So from here t equals 0, it takes t time to reach down. So starting from the same question, t equals 0, the time taken will be capital T. Let's say we want the relation between t and simple t. Okay, so plane is made frictionless. The time taken by the sphere to slip down will be capital T is. We can see here the acceleration is larger. So therefore this T will be higher than T. No? So the answer is higher than T. Is that clear? Okay. So by the way, here you can see the accelerations are independent of the mass. It is independent of the mass and also independent of the radius. So the answer is higher than T because here the acceleration is smaller than when it is rolling, so it takes longer time. So capital T is larger than simple T. 17. Either. So we can write I1 omega 1 equals to I2 omega 2. So I1 of this 2 into omega. So I2 is, so we had to add the moment of inertias 2 plus. So it's a ring mr squared. So the mass is 4 kilogram. 4 into 1 meter squared is 1 squared is 1 into omega 2. So therefore omega 2 is equals to 2 omega divided by 6. So it will be I1 omega 1 is equals to I2. So here uh, 2 plus mr squared 4 into diameter is only 1 meter, so radius is half of it. So it will be 1 over 2 squared, it will be 1 over 4. So 2 over 3. Yeah. Second one, correct. Good. Okay, do this question. A decoration consists of 4 independently rotating sets of small lantern PQRS, which are fixed to a rotating central pole, as shown in figure. All the rotation takes place around vertical axis. Which of the following modes of rotation provides the best stability to the entire decoration? Okay, I will mark this, it's not clear. So here it is rotating this side. This is this direction. This again this direction. Um, this is again this direction. We mark in different color. Red maybe. This in this direction. This is this direction. And this is this direction. Here this is this direction. This is this again this and this direction. This is in the opposite direction. Okay, so choose which is correct. Which one is more stable? No. The answer is fourth one. Okay. I'll ask you a question. Tell me, a bicycle is more stable with at higher speed or lower speed? A bicycle is more stable at higher speed or lower speed? Higher speed. Good. Likewise, now for example, if you take a top, Bambaram. Okay. So tell me, if you take that, it will be stable at higher speed or lower speed? A top is more stable at higher speed or lower speed? Abhishani? Yeah, a top is more stable at high angular velocity or low angular velocity? It is same as the bicycle now. Your bicycle is more stable at higher speed. Likewise, you also may notice if it's having a large speed, it will be stable. No, it will be stay vertical. But when the speed decreases, it becomes more unstable, right? ஒரு பம்பரம் கண்டிப்பா தானே ஃபாஸ்டா சுத்தக்குள்ள வந்து ரொம்ப ஸ்டேபிள் ஆயிக்கும். Even if you try to give a shot, it will be stable. But when the velocity is decreasing, if you give has a small angular velocity, if you give a small kick, it will fall, right? Have you noticed that while playing with bambarams? Okay, so higher the angular momentum, more stable. So out of these, here this everyone has the angular momentum this direction. On the right hand roll, this is also up, this is also up, this is also up, this is also up, and this is also up. So overall angular momentum is maximum here. But if you take this here, you have this one is down, this is up, this is down, this is up, and this is down. So the resultant will be smaller because some are acting downward, some acting upward. But here everything acting upward, so this fourth one is the most stable one. Okay, so let's move on to the next question. Okay, do the 19th one. The figure shows a bicycle wheel which is rotating with large angular velocity omega. About the axle AB, hung from string connected the end A, okay, and holding from end B. If it's released from end B, the end B will fall down and the axle AB becomes vertical. Okay, you had to select the correct one. Yeah, you correct. The answer is the third one. The axle will rotate above the vertical axis through A while AB remains approximately horizontal. So we call that gyroscopic effect. You can just search in YouTube, you will get some videos related to that. It will be nice to watch and knowledgeable. I mean, it will be. I actually recommend you to search on YouTube and watch explanation videos about the gyroscope. You can search gyroscope or you can search gyroscope effect. This effect is due to the angular momentum. Okay. All right. So let's wind up from here. And coming Tuesday, we will be doing the hydrostatics. Okay. All right then. Any questions?